Good afternoon, everybody. Welcome to our webinar. My name is Tim Noka. I help to coordinate all things virtual at ProTech. We appreciate your coming and we appreciate your participation. Joe Fisher is our presenter today. Joe is the founder of his own consulting organization that specializes in secure development processes, developer education, and security testing. Joe has over 25 years of programming and security consulting experience. He is therefore uniquely qualified to present today's topic, and he's very passionate and a big believer in the need to improve web application security. I take it we all feel that way. That's why we're here. Joe has spoken on security at the Open Web Application Security Project, at the Java SIG, and at QCon, all taking place in New York City. He is a certified ethical hacker, certified information systems auditor, and he holds advanced degrees in computer science and business administration. Go ahead, Joe. Thank you all very much for coming.
Great, thank you, Tim. I appreciate that. Glad to be here. Delighted to be partnering with ProTech for this important topic. We have about an hour, and of course security is not an hour-long topic, so we'll do our best to provide an overview of the most critical concepts. Obviously we won't get down into the code, but you should be prepared to understand what to do, if not exactly how to do it, given our overview. If you have, my contact information is on the first slide here. If you have technical questions, please feel free to reach out to me. Otherwise, we'll give you a contact list at the end of the presentation for following up with questions about training and ProTech services and things like that. So let's get right to it. Why are we here? Clearly, if you have IT resources, you have risk. Your IT resources are typically there for some purpose. Maybe it contains sensitive information. Maybe you store intellectual property, strategic plans, anything that you'd rather not have unauthorized access to it. That represents risk to you. The public exposure of that information represents risk to you. A public acknowledgement of a breach might represent considerable liability and damage to your organization. All of these things can be very, very expensive. It's important, therefore, to understand the ROI of information security. And of course, ROI means return on investment. And the idea is just that the money that we might spend on securing our infrastructure, securing our applications, and otherwise making our environment a little more secure and defended is money well spent. One of the ways that we can justify that expenditure is to look at the maximum possible damage that could occur in the event of a breach through a particular system, and then look at the probability of that breach occurring, and that is sometimes referred to as the discounted damage budget. And what we could then do is say, look, we're justified in spending up to that much money investing in the information security either for an application or for our organization or whatever the case may be, depending on how you did the estimates. But it is possible, in short, to calculate the ROI of information security. And that's an important thing for managers and developers to understand because we have to get funding for that portion of our project. The value proposition for secure design and secure development is really very straightforward. You're already spending the money. If you're a development organization, you're likely building product, testing it, finding security problems, and then spending a cycle or an ongoing process of fixing those problems. Very similar in nature to what we encounter with quality assurance and quality control. Short story short, it's cheaper to prevent security flaws than it is to detect and repair them after the fact. So all the same arguments that you would use to justify a quality assurance program, you can use to justify a security program. This is why we're here. Well, where is here? Everything we're going to present today falls within a category of security called application security. Allow me to show you what I mean. This is a graphic that kind of outlines all of the potential security domains, and down at the bottom there you see in orange application security. And of course application security, and this is the whole point of showing you this, is just one aspect of the entire picture, and security cannot exist in a vacuum. All of these areas, or at least many of them, have to be addressed in order for your environment to be truly secure. For example, you can write the perfect ultimately secure application, but if it's running on a platform that has been compromised, it doesn't matter. Your application is compromised. If your environment is secure, but you don't have physical security, somebody can walk up and put a DVD into a hard drive of a server or something like that, then you have lost physical security. The platform won't be secure, the application won't be secure, and so forth. So again, not to get bogged down in the details, but simply to point out application security is just but one aspect of overall security. That having been said, we will focus the remainder of our time on application security. The next slide describes where in the software development lifecycle we have the potential to positively impact the security of our applications. So let's take a look at that. This is not meant to be an entire survey of the software development lifecycle, but rather some spots at which you can make a specific impact. Project initiation is the earliest stages of the project, where we sometimes write what is known as a project charter that describes why we're doing the project, what's the return on investment for the company, for the project as a whole, who are the stakeholders, things like that. That would be the appropriate time from a security point of view to introduce the idea of ROI, to make the ROI argument about security, to make some statements about the value proposition. In other words, in short, to get the budget you need for the security of the project. There's nothing for nothing in this world, and we're all professionals, and we know that if you want a secure product, just as if you want a quality product, you're going to have to spend more time and spend more money, therefore, to achieve that. And that's just the reality of the situation. On the other hand, we want to look at that as an investment and say, if we do that, perhaps we spend less time later fixing these things, repairing these things, throwing away useless product and so forth, and thereby get the benefit of that investment. Another juncture at which we can impact security positively is requirements gathering. And of course we all gather, document, and review requirements because that describes what the application is supposed to do, but it's also the point at which we should be gathering what is known as security requirements. We'll be defining security requirements later, but in short it really means defining the expectations about the application in regards to security. The design phase is another point at which we can impact the security of the application by avoiding, obviously, common vulnerabilities, by reviewing our design with subject matter experts, and making sure that we're going into construction with the most secure design possible. During implementation or construction, we want to make sure that developers are aware of best practices regarding secure development, best practices regarding secure coding in whatever language they happen to be using, and that there are differences across the languages. There's a different set of considerations. There's overlap as well, but there's a different set of considerations in Java than there is in C++ and C than there is in .NET and so forth. During construction, it's our opportunity to take advantage of static code analysis tools, dynamic analysis tools, to scan the software, examine it at runtime, and find any issues that are emerging during construction. Of course, testing is an opportunity, just as it is for quality, to find security problems. This is where we would do security testing and make sure that our security requirements had been fulfilled. This would also be an opportunity where we could do some ad hoc testing, some less structured testing that would perhaps include things like testing to see if somebody could break into the application, penetration testing, if you will, or ethical hacking. Finally, during maintenance, and this is sometimes overlooked, there's the opportunity as maintainers work with the code and fix bugs or make enhancements and so forth, that they would introduce security flaws into the product. So once again, this is an opportunity through awareness, static analysis tools, configuration management, and so forth to make sure that the application actually remains secure, that we don't jeopardize the security of the application in the maintenance phase. So here are some critical things. We're going to need to define security requirements in order to have a secure product, period. We're going to need to vigorously validate what we call untrusted input. This basically means any input that comes into the program, and we'll define it shortly in a little more detail, but any inputs that come into the program, we need to make sure that they meet the program's expectations. What are the program's expectations regarding inputs? See number 1. They should be defined in the security requirements. So without, again, we'll come back numerous times to that point, without security requirements you cannot really achieve a secure product. With security requirements you at least stand a shot at it, but you need to do these other things as well. So validating untrusted input, sanitizing data as necessary, number 3. Sanitizing means encoding data so that it can be safely processed by whatever storage mechanism, like a database that you have, or It depends on really what the destination and processing of the data is going to be. You will encode it specifically for that environment to protect that environment from potentially malicious data. Number 4, protect sensitive information. Well, we have to define what sensitive information is, and then think about strategies as to how to protect it when it's in storage, when it's in transit, perhaps even when it's in the application's memory. We want to, in step 5, or critical thing number 5, define and maintain trust zones. This has to do with, the different domains in your architecture. For example, the database or other interacting systems, file system. To what degree do you trust the contents of that? Users are actually a trust zone. To what degree do you trust or not trust what comes out of those zones? And of course, whenever data crosses a zone boundary, we're going to need to look at that and validate it to make sure that it is appropriate for the zone it's going into. Number 6. Manage application state. This has to do with regulating the navigation of your application. As a user works their way through from page to page within your application, making sure that we're tracking that and that at any point in time we can answer the question, does this transition make sense and should we allow it? Number 7, conduct application security testing. Have a security test plan that goes alongside of your quality test plan, and that includes, as we mentioned before, structured and unstructured types of tests. Critical thing 1, define security requirements. This has to do with roles and permissions of users, how we will carry out authentication, what are the interfaces with other systems. Protocols really mean the rules of engagement with other systems, the vocabulary and the rules of grammar for interacting with other systems, expectations regarding inputs, commitments regarding outputs that we'll produce. All of these should be defined in security requirements to a very detailed degree. And to the extent that they are not right now in your organization or on your project, you need to think hard about that, because once again, many of the things that we'll be telling you that you need to do in order to secure your application ultimately are traceable right back to these points. Some things I might add to this: host system expectations, failure scenarios, who and what features and capabilities will we have, accounts, what permissions will the accounts have that operate on behalf of the application, perhaps even what relevant policies and procedures would be applicable to the application. Your organization should have some security policies and procedures. For example, maybe a password policy or something like that. Rather than reinvent that and redocument it here for the application, we should simply be able to refer back to that and say, yeah, this application will be consistent with the organization's password policy, and any other policy that happens to be relevant and documented as a security policy. The bottom line is that security requirements should be usable by the security test planning and execution organization, who's ever going to do that, design and document the test plan, who's ever going to do the security testing, and also by application designers and developers, because they need to consume this document and make use of it and understand it and ultimately encode it. The bottom line, again, you cannot adequately secure your application without security requirements. Your choice is either to define security requirements up front at the beginning of the project, or to do so incrementally and painfully, piecemeal, throughout testing and maintenance in an ongoing fashion. Second thing we emphasized was to vigorously validate untrusted input. What is untrusted input? By this we mean HTTP headers, user form data, data that's coming up from forms in your application, cookies, environment variables, file contents, data that's coming from other systems, basically anything that has to be validated and should be validated. It's incredible to me that in this modern day, in this day and age, I still look at applications and I see applications reading directly from the HTTP request and using it without validating what's coming in. And you can spoof that information very easily by putting a proxy in between your client, meaning the browser, and the server that it's submitting the URL to. So you simply cannot trust user data. You cannot trust the client. Everything has to be validated on the server. Well, what does validation mean? How do we validate things? It means that we look at the data type of the input, the size, if it's numeric, what's the minimum and maximum bound, the range, the pattern perhaps. If it's a telephone number, does it look like a telephone number? If it's a social security number, does it look like one? Perhaps it's an enumeration of possible values that we can check. But the point is we use any or all of those in combination to convince ourselves that that's exactly what it's meeting our expectations. There's something else that's mentioned here. Is the data expected at that point in time in the application? Is it required at that point in time in the application? It's equally wrong to accept something that you're not expecting than as it is to reject something that's not correct. So we have to be sensitive to extraneous information as well. Down the bottom, last bullet, whitelist validation. What this means is that when we talk about validation, we define what's acceptable and we reject everything else. This is in contrast to blacklist validation, in which we define what we don't want. And the reason why whitelist validation is superior to blacklist validation is it's much easier to define what you want rather than to continually evolve what you don't want, a definition of what you don't want. Bottom line is that validating your input is your best defense against a number of common vulnerabilities, including things like buffer overflow, in which a large amount of data is provided, far more than was expected, and it is used to basically swamp the computer's memory. A very serious type of vulnerability when it exists, because it very often leads to what is known as the arbitrary or execution of arbitrary code, which basically means that the attacker has provided their own program now within the context of your program and is running their own code within your program. Very scary scenario. One other point here on how to handle validation failure. We need to detect invalid data. We need to inform the user or the other system that we have detected a problem. And we need to respond to it. Clearly indicate that we're under attack or we're being probed. We want to respond a little more aggressively in those cases. Another thing we're encouraging you to do as critical is to sanitize your data. That's defined at the bottom of this slide. To encode and decode characters to render them safe for whatever context they're going to appear in. To do this properly, we have to understand the context, the processing, and the ultimate destination of the data. For example, maybe a particular data item is going to be used to execute a command, or maybe it's an argument to a command that will be executed. So we have to be sensitive to the rules about the operating system, command line execution within the operating system. We have to think about what meta characters are defined in that environment. Maybe it's Windows, maybe it's Linux, maybe it's some other environment. Perhaps our data is going to be inserted into a database, very common scenario, and we have to be a little bit sensitive to things like single quotes, which are characters that have special meaning to SQL, to structured query language. Maybe our destination is ultimately for a web page. We're going to take the information that the user has provided to us and reflect it back somehow onto a web page. Again, if the user provides us with maliciously crafted data, they might be able to execute their own commands in the operating system. They might be able to execute arbitrary SQL in the database. They may be able to execute JavaScript in the web browser, all things that were not intended by our designer or our program. So injection attacks are very often the result of failure to sanitize data. And sanitizing data, encoding it as appropriate for its processing and destination, is going to be our best defense against injection attacks. Protecting sensitive information. Well, you probably already have an intuitive understanding of what information is sensitive in your domain, but you really want to define that so that everybody is aware of it. And make design decisions appropriately. You're going to have information that's sensitive in the domain, and by that, that could mean client information, patient information, customer information, financial data, intellectual property, strategic plans. The world is full of sensitive information. But it could also include application-sensitive information. And by that we mean the design of your database. Maybe that's not something you want out there in the world, because if I understand your schema, your database schema, that puts me as a potential attacker in a much better, more informed position to exploit that information. So we need to be a little bit sensitive about how our application works, how it's designed, and really not give away any information that would facilitate or enable attackers. We need to, in the course of our design, decide how we're going to protect that information in storage. Are we going to encrypt it? Are we going to somehow obfuscate or cloud it? Are we going to, what are we going to do in application memory when we have something like a password that's residing in memory, or a social security number or something like that? Typically, we want to blank out the memory before we put something in there, use it for the sensitive information, and then blank out the memory as soon as we can afterward. How do we protect information in transit, meaning as it is communicated between components in the system, between systems? This would be where we use, again, encryption or secure socket layers or some other technology to make sure that sensitive information is not transmitted in clear text. Another critical item, defining and maintaining trust zones. By that we mean, first of all, defining what the trust zones are, but ultimately it's a strategy for dividing and conquering the security space. Understand the degree to which you trust database content. Now, typically we want to be able to trust what's in our database, meaning that we don't want to put anything in the database that hasn't been properly validated and that we can't work with. So you want to validate things on the way in and then put them in the database only when they're safely validated and sanitized. It might be the case that some other interfacing systems, we trust them, others we don't, and we have to validate and sanitize accordingly. We typically don't trust anything that comes from users because users can be malicious, user machines can be compromised unbeknownst to them. So we really have a very low degree of trust with our user community. And then, of course, files on the file system. May or may not trust the contents of those depending on who created them, when, and to what degree those have been validated. So we have to look at those things and understand for our particular application and design the degree to which we trust that information, and then correspondingly how do we validate so we protect our application. And that's what the bottom line here is. Manage application state. This is an interesting one. And a lot of organizations, a lot of designs don't do this properly, and let me explain what I mean by this. It means to monitor and track each user as they navigate their way through the application. You can envision your application, your web application, as a finite state diagram where each page is in fact a state, a different state. And that as the user moves from page to page, they are transitioning between those states. And at any point in time, when it's time to do a transition, when the user clicks on a link and is requesting to see another page or activate a feature or something like that, we need to ask who is the user and what are they authorized to do? What state are they currently in, and what state are they trying to get to? And only then can we make a decision, a determination about whether or not that's permissible and possible, given the security that we've imposed on the application. So the trick to that, of course, is to understand the information flow, understand what transitions are permitted at each state, and then also understand the information flow that's associated with that transition. So is certain information required along with that transition? Is certain information optional? And anything above and beyond that we would consider suspicious. And then, of course, the bottom line is to enforce the rules about application state. This puts us in a position to head off numerous types of attacks, such as cross-site request forgery and various privilege escalation attacks, because we simply won't allow the user to access a page that doesn't make sense given the context that they're in at that particular time. Conduct application security testing. There are numerous static analysis tools, static meaning you run them against your source code, your program is not running at the time, that can be used to uncover and detect security vulnerabilities and potential problems. There are false positives, and there's a lot of extraneous information that comes from these tools. I'm not going to endorse any particular tool, but I can mention two that are very popular and very effective. HP has a tool called Fortify. IBM has a tool called AppScan, both of which are used extensively and have a large market share and are very effective and consistently updated. Those tools have a place in your software development lifecycle, and if you're building software right now and you're not scanning your source code with some sort of security tool, you're making a mistake. There's plan testing, that we look at our security requirements and we develop a test plan based on that, including positive and negative testing to make sure that the application succeeds and is successful and meets expectations when things go well, and that it also fails properly when things don't go so well, so that it succeeds when it should and it fails when it should. And also, by implication, that it fails safe, so that when things do go badly, the application still maintains its integrity, still maintains its security. Down the bottom, there's also an ad hoc or less structured type of testing that we will do, ethical hacking, if you will, or penetration testing, where we can use tools to explore potential vulnerabilities in the application, looking for things like cross-site scripting, looking for things like SQL injection vulnerabilities and so forth. There are tools to help us with that. And then ultimately there's the manual approach, where you take seasoned hackers and allow them to try and breach your application, either in a white box manner, in which they're working with your development staff, or in a black box manner, in which case they're really just approaching the application like a real hacker would. So, having now talked about the critical things, let's take a look at what is known as the OWASP Top 10. We promised you a talk on common vulnerabilities, and we wouldn't be doing our job if we didn't talk about the OWASP Top 10. OWASP stands for the Open Web Application Security Project. It's a global organization of developers and security folks that are dedicated to improving the security of web applications. Every year, they solicit input from a number of large security companies, and they compile a list of the most common vulnerabilities that were found that year in web applications. Sadly, the same suspects, the usual suspects, show up year after year after year. This is the 2013 list, and it includes the following. The first one is known as injection, and this means that maliciously crafted input has been provided or can be provided to the program, and it results in either execution, unexpected, unintended execution in the database, or on the command line if it's command injection, or cross-site scripting, which is number 3. Cross-site scripting is actually an injection attack because we're providing input to the program that is somehow reflected back onto a web page and then executed as either JavaScript or XML or something like that. And so injection is definitely the number one most common, and these are in terms of frequency or occurrence, the most common type of vulnerability found in web applications. Second one is broken authentication and session management. This has to do with passwords and whether or not authentication. Of course, authentication is the means by which we prove or determine that somebody is who they say they are. If I come to the application and I say I'm the user Joe Fisher, it's not going to take my word for it. It's going to say prove it. It's going to ask me for a password, or it's going to ask me for a password and a token ID or something to convince the system that I am who I say I am. That's the process of authentication. Any trick or means by which we could bypass authentication or, following authentication, escalate our privileges to maybe assume the role of an administrator or higher authority would be a problem. Session management has to do with once we're logged in, authenticated, and using the system is probably maintaining some state about the information we've provided previously so that it knows, that I've already logged in. It's not going to keep asking me to log in again and again. It's going to remember certain things. That's session management. And there's certain things that we can do well when it regards to session management, certain things that we can do poorly, and apparently there's enough things being done poorly that this makes number 2 on our list. By the way, we're going to revisit each one of these and talk about what you can do to mitigate those vulnerabilities or avoid them altogether. Number 3 is cross-site scripting. 2 variations or flavors of that. One is called reflected cross-site scripting. What that means is that an input comes into the system, which is then reflected back out in a response. The way that, of course, a web application is going to work is that the user is going to request a page. That's going to be called a request. The server is going to process that request and issue back a response, which is typically another page. Reflected cross-site scripting is where the response contains some input that the server then turns around and returns as part of the response without validating it or otherwise encoding it, so that, in fact, where the application might have asked for a name or an address or something like that, but I typed in some JavaScript code and sent that up as the name, and it gets reflected back to the browser. It may very well execute that. The browser may execute that as JavaScript, and all of a sudden we have unintentional, program executing within our own design. So there's another type of cross-site scripting called persistent cross-site scripting, and this has to do when we take the input that an application provides and we put it into the database. And then subsequently we reflect that back to other users either when they query that information or when we display, other pages. And that's particularly nefarious and troubling because it means that many, many users could see the effects of a cross-site scripting attack. In other words, consider like a bulletin board application where users could enter some information on a bulletin board, and some of that information might be malicious, but then it gets put into a database and reflected to everybody who comes and looks at that page. So that can be a particularly, magnifying effect of a cross-site scripting attack. Number 4, insecure direct object references. This refers to things like URLs, or file names, or user IDs, or anything that the user might provide us with as an input directly reference some system resource. The problem with that is insecure use of that would be if we don't validate it, and we are asking them perhaps for a file name, and they, instead of providing a file name that we expect, they provide us with a path to a file that we don't expect, that's not part of the application, but we fail to detect that and we process it anyway. So path traversal vulnerability is an example of number 4. But the way that we handle that is, well, we'll talk about how to handle it, but it really has to do with allowing the user to specify a system resource and not validating that it is an appropriate resource for our application. Number 5, security misconfiguration has to do with how the platform settings are configured. Maybe it's the web server, maybe it's the operating system, maybe it's some other component within the application, but something isn't configured properly. It might even be a firewall or something isn't configured properly, and it's allowing a vulnerability to exist. Number 5 very often is beyond the scope of our application, but nonetheless impacts the security of the application. Number 6, sensitive data exposure, I think is fairly self-explanatory. Number 7, missing function-level access control. This means that the roles and permissions that have been defined for the application are not being properly enforced. Maybe the account is operating on behalf of the application. The operating system account is not being used properly. Maybe there's some sort of privilege escalation taking place. But for whatever reason, the proper roles and responsibilities and the permissions that go along with that are not being enforced. Number 8, cross-site request forgery is a very I don't know, what do you call it, insidious type of attack. It takes advantage of a user who is already authenticated to a system. So the scenario would go along with something like you're using your banking application, you're logged in, you're authenticated to your banking application. I send you an email, probably a phishing type of email. It contains a link. The link itself would be a dead giveaway that what I'm going to do is that URL is actually pointing to the application that you're using and references a transaction, will cause a transaction to occur that would only be possible if you were authenticated and logged into that application. If I can get you to activate that link, I can get you to actually initiate a transaction within that application on my behalf, perhaps. And if I disguise this in such a way that you might click on the link or move over the link and somehow activate it without realizing it, I may actually be able to get you to do something without you realizing it within an application that you're logged into and authenticated in on my behalf, some malicious activity. So it's a very scary thing. And it's very commonly partnered up with some sort of email phishing attack. Number 9, using known vulnerable components. The fact of the matter is that, well, anybody who uses Windows knows this with a super patch Tuesdays, that every day new vulnerabilities are found in operating systems, in products, in components, and so forth. And the manufacturers are notified and eventually issue an update that patches that particular vulnerability. Problem is, if you don't update your environment and incorporate that new release into your environment, you are using a known vulnerable component. So once again, you could have done a fine job securing your application, but if the operating system hasn't been patched, they might be able to compromise the operating system and thereby compromise your application or your data. If your application utilizes, I don't know, third-party components, and you're using older versions of those components that haven't been updated, there might be known vulnerabilities in the components that you're using. Once again, you're vulnerable, kind of through no fault of your own, but kind of through fault of your own, that there's a way to get at your sensitive information in your data. Finally, number 10, unvalidated redirects and forwards. What that means is that your application issues a URL request to the server for a resource, and for whatever reason, the system comes back and says, no, what you really want is the following, and they redirect the browser to go someplace else. The problem is that sometimes designers will take untrusted input that's coming up with the request, and they'll use that to craft the URL that they're redirecting the browser to go to. Hence, it's unvalidated redirect. In other words, it might be a case where I could provide some information in the request that would cause the response to go someplace else, potentially to a malicious website. Again, if I'm clever, unbeknownst to the actual user of the application. So let's talk about how we fix these things.
Hey Joe, we do have one question. It does go to the last slide. It goes to bullet number 3, and it says, could you give an example of cross-site scripting for database again, please?
Sure. Cross-site scripting as it applies to database storage would be persistent cross-site scripting, where the user provides us with maliciously crafted input, which we then store, presumably without validating it or encoding it. We store it into the database as part of their information, so that in subsequent use, the application will retrieve that information and display it either back to them and potentially to many other users. So the reason why cross-site scripting, persistent cross-site scripting, is so dangerous and so damning is because we've kind of permanently archived the malicious data, and now every time we retrieve it from the database and show it to somebody, we are again putting them at risk. Okay, so here's a very valuable, next couple of slides, very valuable information, because it basically takes the top 10 OWASP vulnerabilities and it says, now what can you do to address those? What can you do to mitigate those vulnerabilities? And there's a number of things I want to point out first that obviously are going to be in the background and would be valuable no matter what. And the first is training and awareness of your developer community. It's very difficult to protect against things that you're not aware of. You don't know what you don't know. So first and foremost, you have to make sure that your developer community is fully aware of, at the very least, the OWASP top 10, and then ideally beyond that, the broader security perspective, so that they are designing consistently with security in mind. Defining security requirements are going to drive everything else that we do. You'll see the word validation appear over and over again, input validation, input validation, input validation. You can only validate against a definition of what the input is supposed to look like. If it hasn't been defined in the security requirements, you can't hold your developers responsible for separating good data from bad data, malicious data from acceptable data, because nobody's defined it. So security requirements are clearly an important thing. A focus on security throughout the SDLC, and that includes on behalf of management, a commitment by management to support security efforts, and security testing at each and every stage of product development. So all of those things are going to kind of be in the background as we go through this. With regard to injection, if you validate the data and you sanitize the data above and beyond what the validation already does, you can avoid injection attacks. But of course, you have to know where your data is going to be used. Is it going to the database? Is it going to be used to execute a command? Is it going back to the browser as part of a response? That matters, because the validation and particularly the sanitization that we do has to be appropriate for the context. Static and dynamic analysis tools also are very good now at picking up different types of injection scenarios. Actually, spooky how good some of the tools are. Broken authentication and session management. This is a matter of doing a good design and reviewing that design with subject matter experts. If you don't have the expertise in-house, that's a perfect use for a consultant. You get them in, you suck their brain for the purposes of broken authentication and session management, and then out the door they go, and you bring them back when you need them. But don't be afraid to bring in the people who have the expertise to get it right the first time. Cross-site scripting. Validation, output encoding. By output encoding, of course, we mean the different types of encoding that you need to do based on the context in which that data will appear. That's a little bit nebulous. Let me explain what I mean. When you're taking data, and particularly untrusted data that has come from the user, even if you validated it, you still need to do certain things to prevent that data from being evaluated by a browser, either as HTML or as JavaScript, even more frightening as JavaScript. So the types of encoding that you might find yourself doing include HTML entity encoding, HTML attribute encoding, JavaScript encoding, URL encoding. It all depends on where you're putting that information into the response. Different contexts require a different encoding approach. And of course, there are even places that, given all of the above, it is never safe to put untrusted input into your response. So there's just certain situations where it's too dangerous to put things in certain places. So there's a whole set of rules about that, and we can't go into it now, but it is possible to avoid cross-site scripting, but it's probably one of the most complex challenges that you'll face from a web security point of view. Number 4, insecure direct object references. Well, we need to validate those inputs when it comes up, but we also want to use something called indirect references. Rather than asking them for a file name directly, maybe we list the files and give them a number. They can choose a number, and they send up a number, and we use that number to do a lookup to find the actual resource. Maybe we don't give them the real file names, but we obscure the real file names on the system to give them some synonym for them. In other words, design around the vulnerability so that they cannot provide malicious input and fool our application into processing things that it shouldn't. Number 5, security misconfiguration. That goes directly to security requirements. Setting down in black and white any expectations about the operating system, about the platform, about the configuration of all of the above, accounts, permissions, and so forth, and perhaps even conducting reviews and audits of that environment to make sure that it not only is set up properly initially, but it remains set up properly and secure. Preventing sensitive data exposure. Again, that's design reviews, and to some extent the static analysis tools will help you with that as well. Some of the static analysis tools are very good at detecting things like sensitive information, passwords, social security numbers, IDs in memory, and things like that. And will yell at you if you don't deal with them properly. Number 7, missing function level access control. This has to do with defining and enforcing roles and permissions and keeping track of state as the user navigates through the program, so that at any point in the execution we can say, who are you, what state are you in the application, and do you have permission to do what you're trying to do right now. Preventing cross-site request forgery. This is a matter of design. There's a little design technique or trick that we use called random token passing. And what it basically means is every time the server responds back to the client, it provides a randomly generated token, and then when the client responds with its next request back to the server validates that it's being given back the token that it just passed to the client. In other words, it's a way of validating that I'm still having a conversation with who I thought I was having a conversation with. That, of course, if you remember back when we talked about cross-site request forgery, if the user receives a link and they inadvertently click or activate a link which isn't technically part of the program, but which is a legitimate URL for that program, the random token would not be part of that link because the attacker wouldn't know at that particular point in time what the random token should look like. So therefore the URL would be rejected because it didn't have the secret token, and thereby defeat the cross-site request forgery. So it's a design kind of consideration that we put in there. And design reviews, and again, even static code analysis tools will detect the potential for cross-site request forgery. They won't typically detect the solution to it. You'll have to validate that yourself. And then, of course, security testing. There's nothing stopping us from peppering our running application with URLs to see if we can get it to do something that it's not expecting to do, not intending to do. Number 9, preventing the use of known vulnerable components. Well, this requires a security focus in maintenance. Clearly, during design and development, we should be very focused on using the latest and greatest software and platform for our development. But going forward is when things tend to slip. When we get into the maintenance phase of the program lifecycle, that's when, over a longer period of time, the ground starts shifting. Operating system patches are released, application component are updated, and so forth. And if we're not alert and vigilant to that, then we won't update our environment, and we will fall victim to number 9. And sadly, there's numerous resources out on the internet that you can search by operating system version, by application and version, and it will come back and say, oh, here are the vulnerabilities that are known for that. And there's tools, public domain, free tools that will actually craft exploits for you so that you can attack such systems when they're known to be vulnerable. Number 10, unvalidated redirects and forwards. Well, there's our old friend input validation, and of course design and design reviews as well. So the idea here is that there are absolutely things that we can do to avoid the most common vulnerabilities, and most of them have to do with input validation, sanitization of data, and maintaining and tracking state. And if you do those 3 things, you're well on your way. It's not all you have to do, but it's necessary but not sufficient. Down the bottom of the page, I referenced the OWASP Top 10 reference. If you are developing web applications and you are not familiar with OWASP, you absolutely have to become familiar with OWASP. It's an enormous set of valuable documentation, tools, It's a community. It's a global community. It's also a local community. So I would strongly encourage you to get familiar with that group and its resources, and even to participate. So let's just wrap up as we wind up the hour. In terms of management, what can management do to increase security? Well, be committed to it. Make sure that developers are aware of security topics. Make sure that requirements are defined. Make sure that design reviews and security testing take place. What can developers and designers do? Obviously implement the security requirements, enforce roles and permissions, validate untrusted inputs. Watch out, I'm jumping ahead a little bit, but watch out, define and maintain trust zones, sanitize inputs as necessary for the subsequent processing, protect sensitive information, and maintain, track, monitor, and enforce, most importantly, application state. If you do all those things, you are well along the path towards having a secure application. If you're sitting here listening to me and you're not doing any of those things, or you're only doing a few of them and very haphazardly, then your application is unquestionably at risk, and you need to seriously think about what you're going to do to fix that. So with that having been said, we will wrap up. We will take questions, and I appreciate everybody's time on this. I hope we shared some valuable information. That is my concern, is you're going to devote an hour to this of your time. I want to make sure that you found it valuable and informative. Hopefully that was the case. There's information here about how to contact ProTech. We have a number of classes on the catalog regarding security, including general security awareness, including specific things like NERC SIP, HIPAA, PCI classes, including web application security and secure coding classes. I won't go through the whole list, but there's a whole number of options that you have available to you depending on what your needs are. So with that, I will stop here and solicit questions, and thank everyone for your time and attendance.
Thank you all very much for coming. It's greatly appreciated. Joe and I will continue to hang around through the top of the hour in case there are any questions. Don't hesitate to put them into the question area. All right, Joe, we got one that is a little more than just a thank you for a great presentation. Can you tell me what you know about the merits of Fortify?
Fortify is really a world-class tool. I'm actually using it at a client location right now, and I'm very impressed with it. It does generate false positives, but it finds things that it will surprise you that a scanning tool can detect. It's very broad in its capabilities, and they keep it up to date, so that when new vulnerabilities are published and become public, very quickly those rules are incorporated into the tool, and you begin to see the benefits of those in your scans. So yeah, I would feel comfortable endorsing Fortify as a very reasonable SCA solution.
Very good. Thank you very much. Is there any code samples to showcase injection vulnerability? I mean, how we might miss out on certain simple validation, which might be a security threat.
Well, there are examples out there in the world. I hadn't prepared any here, but the classic type of thing would be, if I can bring up a window here, the classic type of thing would be where the user is intended to enter their name, and they put in, so the prompt might be name : and there I'm expected to say, my name is Joe, but I also put in a single quote, and then I say something like, or 1 = 1, semicolon. And what that does then, when I submit that as my name, it actually will interfere with the SQL under certain circumstances, so that the entire query is going to turn out to be true no matter what, because 1 is always equal to 1. So if this were some sort of conditional query, perhaps that's authenticating me, it may come back true even though I didn't put in the proper password, thereby bypassing authentication. So it's a very simple example, but a single quote, a random single quote in a field is not an uncommon way to determine whether or not your application is properly handling SQL injection. At least I could say it this way: if it chokes on a single quote in a field anywhere, it's probably not properly validating and sanitizing data for the database. Similar examples I could come up with for command injection and for cross-site scripting.
Thank you all very much for coming to our presentation today, and I hope you all have a great day.
Great. Thank you all.